Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ali Fakir bin Bahrain, matrix number 2024629602 from group CDCS 1121B. For today, I'll be explaining about one of the chapter in differentiation, which is the applied maximum and minimum. The function of applied maximum or minimum is to find the optimum value. Let's take a deep look at this chapter. In order for us to analyze the function, we have to find the critical point. Therefore, we are required to differentiate the function to get the critical value. This derivative represents the rate of change of the function. Secondly, set the derivative equal to 0 and solve for the variable. The solutions are called critical point. These are the point where the function slope is 0, indicating potential maxima or minima, or known as extremum value. After that, we are required to do the second derivative test. This test is to determine whether each critical point is maximum, minimum, or saddle. If the second derivative is positive at critical point, the local function is a local minima. If the second derivative test is negative at critical point, the function has a local maximum. So, let's take a look of example.
Bismillahirrahmanirrahim. My name is Aufa Shafina binti Muhammad Afzaini. I'm from CDCS 1121B 2024801768. Now let's take a look at an example for the first example. So first example is about a rectangular box with a square base and no top, which is have volume of 108 centimeter cube. And so the question is, find the dimension for the box that require the least amount of material. Okay, now we know from the question, when it said the least amount of material, we know that it wants the minimum of the material. So the function that is to be minimized is the surface area, while the volume remains fixed at 108 centimeter cube. Now let's start the calculation. So it gives volume equal to 108 centimeter cube. Okay, so we want to find the equation that equal to volume. So our volume equal to x multiple y and equal to x square y. You know, from here x multiple x and y. This is the volume. So the volume, and we equal to x square y equal to 108. And from this equation, we find the value of y and equal to 108 over x squared. And now we want to find the surface area. So the area, we know that this is the box without top, and it only have one surface and four sides of the box. So we make the formula area equal to x squared plus 4xy. Then we substitute the value of y into this equation, and it's equal to x squared plus 4x 108 over x squared, and lastly the area equal to x squared plus 432 over x. We will find the minimum. Okay, so the first step, we have to find the derivative. So from the formula, area equals to x squared plus 432x. We do the derivative test, and dA over dx equal to 2x minus 432 over x squared. From this, we let the derivative equal to 0. So when we equal to 0, we will get x equal to 6. And now we know that the value of x is 6. First, from this, we will do the second derivative test, and then we get 2 plus 864 over x cube. So from this, we will substitute the value of x here. We substitute through this, and then we get 2 plus 864 over 63. And now we know, and then we get the value is 6. So we know if the value is greater than 6, that is a minimum. We substitute the x into this equation. Y equal to 108 over 62, and we get 3 centimeter. Hence, the dimensions of the box that require the least amount of material are a length of width, which is 6 centimeter cube, and height of 3 centimeter cube. That's all from me. Thank you.
A rectangular field adjacent to a river is to be enclosed. So this is the rectangular field. Fencing along the river costs 5, while other sides are $3. So we label this one as X, and this as Y. Since we want to know the sum of the cost, we need to add 5 with 3. But the cost of $3 is here, and here. So we need to plus this one with this and multiply with 3 to get the equation 1. We know that area equals to length times width. So this is the length and this is the width. And since the equation has already given our area, we just put it in our equation. X times width equals to 1200. After that, just bring x to the other side, so that area will be in terms of x. After we get the y, we can substitute y into equation 1. Then this will be the answer. From this equation, we derive it to identify the increasing or decreasing interval. And this is the answer for the first derivative. We need to equal it with 0 to find the x, which is 30. After we get the x, we do the second derivative test. Bring the first derivative test equation here and derive it. So we know that second derivative test is to find maximum or minimum point. Since this is more than 0, it is a minimum point. 30 into the equation and we will get 40. This is the answer.
From the first example, it shows that the application of differentiation is applied to minimize the surface area while the volume remains unchanged. It's amazingly helpful in solving many problems in our daily life. For instance, producer can maximize the space to load the stock in the store. As for the second example, the application of differentiation really helpful to find the best way to optimize the outcome with the minimum cost. Overall, it can be said that the application of differentiation in maximum and minimum can be implemented to solve many problems by providing the optimum solution in our daily life.